Welcome back to the deep dive. We're constantly swimming in information, so we try to cut through that noise and get to the core insights. Today, we're looking at solar power. It's huge, obviously, but there's always that nagging question. What happens when it's cloudy or, raining?
Right, the intermittency problem.
Exactly.
Yeah.
So we found this really fascinating potential solution. They're calling them rain-powered solar panels. Sounds a bit sci-fi, doesn't it?
It really does.
We're going to unpack how this could actually work, especially for a place like Quincy, Massachusetts, which needs green energy but also gets its fair share of rough weather. The goal here is figuring out if this can crack that intermittency challenge.
That's the core idea. Basically, you're combining standard solar panels with something called Tribo electric nanogenerators, 10 AINs for short. The aim is continuous power generation, rain or shine.
Okay, 10 AINs. That sounds like the key piece here. So how do these things actually work? I mean, getting electricity from raindrops. Yeah. It still sounds pretty wild to me.
Yeah, it's not quite magic, but it's very clever physics. Think about static electricity, like rubbing a balloon on your hair.
Okay. Yep.
TENS use a similar principle called liquid-solid contact electrification. So when a raindrop hits the special surface coated with Tang material, the friction creates a charge imbalance.
Ah, okay.
And that imbalance generates a small electrical current.
And how does that actually fit with a normal solar panel? Are they separate systems?
No, and that's the really interesting part. They've developed these hybrid systems. The Tang layer actually sits right on top of the solar panel.
On top? Doesn't that block the sun?
That was the challenge. But researchers like those at Tsuchiya University have made these Tang films transparent. We're talking like 90% light transmittance.
Wow. Okay, so sunlight gets through mostly, and then when it rains.
Exactly. When it rains, the Tang layer starts generating power from the impact of the drops.
I saw some numbers from Tsinghua University and MIT, something about 385% efficiency. That sounds, impossible, like perpetual motion.
Right. Yeah, that needs context. The 385% isn't creating energy from nothing. It refers to how efficiently the TEN converts the mechanical energy of the raindrop impact into electrical energy. It's a measure of how good it is at harvesting that specific type of energy, showing massive gains compared to older designs, especially for places like New England.
Which gets, 47 inches of rain a year?
Precisely. That much rain makes it a prime candidate.
Okay, that makes sense. So let's zoom in on Quincy, Massachusetts. Why is it such a good test case?
Well, think about Quincy's weather. You've got those humid summers, sure, but also nor'easters, lots of cloudy days, and that significant rainfall.
Right.
On those overcast days, regular solar panel efficiency can drop maybe 10% to 25%. That's where the tanks come in.
So the rain power compensates.
Exactly. Even if a 5-kilowatt hybrid system only generates, say, 325 microwatts from the 10 during heavy rain, which sounds tiny, it's crucial because it's offsetting that loss from the solar panel. It provides a baseline power source when the sun isn't cooperating.
And I saw some simulations for Quincy. A 2,000 square foot roof, potentially saving over $15,000 across 20 years and payback in maybe 8 years. That's pretty significant.
It really is. Economically, yes, adding TENs might mean a 10-15% higher upfront cost.
Okay, that's a consideration.
You've got things like the federal tax credit, 30% right there. Plus, Massachusetts has state programs like SMART and net metering. So that hypothetical 5-kilowatt system cost maybe $14,350 could drop closer to $10,000 after the federal credit alone.
That makes a big difference.
Absolutely. And beyond the direct savings, think longer term, less reliance on the grid, more resilience during storms. That's huge for coastal areas like Hasneck and Quincy that deal with flooding.
And the environmental angle.
Well, obviously less fossil fuel reliance. It can also help reduce the urban heat island effect, and it fits right into green infrastructure goals, and you're essentially repurposing stormwater runoff.
Okay, it sounds incredibly promising, but this is still pretty new tech. What are the hurdles, the bumps in the road?
There are definitely challenges. Scaling up is one. Right now, when you link multiple Tang panels together, something called coupling capacitance can actually reduce the overall efficiency by maybe 15-20%.
Mm-hmm.
And for a coastal place like Quincy, salt water is an issue. Salt can corrode or degrade the special materials, so you'd need robust hydrophobic coatings. Think Wollaston Beach on a stormy day.
Right, the salt spray. And what about rules and regulations?
That's another big one. Quincy's current zoning laws are really built around traditional solar. They don't necessarily account for these hybrid systems yet.
So policy needs to catch up.
Pretty much. One idea is amending the state's Green Communities Act to maybe include subsidies for tanks like they do for solar, but, that requires pushing things forward.
Which means more research and development.
Definitely. Collaboration is key here. Think partnerships with local universities, maybe UMass Boston, to really nail down the technology and address these issues. Kind of like how MIT and Stanford work together on that passive desalination tech.
So it's clear this isn't just a gimmick. Rain-powered solar, these hybrid systems, they really could be transformative for a city like Quincy, mixing renewable power with much-needed climate resilience.
It really pulls those two threads together, which leads to a bigger thought, maybe for you listening. Considering Quincy's specific situation, coastal, rainy, forward-thinking on energy, how might adopting these kinds of dual-mode systems change how we even think about sustainable cities, especially those on the coast facing down, well, increasingly unpredictable weather?